All right, we're going to do error propagation. Now, propagation means to carry forward, or actually, in biological terms, it means to reproduce. But in terms of error, we're just keeping our error as we go. So we're going to do calculations, normal calculations that you've done, but with uncertainties, there are some complications. So we need to make sure we do it right. What we need to know is we need to know about the absolute uncertainty, which is going to be that the margin of uncertainty associated with the result. That's normally what you see, like 0 plus or minus 0.1. And then the percent uncertainty, which is going to be the uncertainty divided by the value times 100. Okay, so I'll give you a second to, you'll figure out what it means in a sec. So the absolute uncertainty, and for this one would be plus or minus 1 milliliter. Sorry that I did that kind of weird. And then the relative uncertainty would be 1 divided by 12 times 100. All right, because that would be the percent uncertainty. So you just basically are taking the percent, 8.31%. And that's telling you that 8.31%, I mean, that uncertainty makes up for 8.3% of your absolute one. Now, for B, that's absolute 0.01. And your relative is going to be, my goodness. Slow down, Mr. Russell. 0.01 divided by 1.04 times 100, and that gives you 0.962. Now, you'll see why later that it's not going to make a big difference on how many sig figs you have. So on this one, your absolute uncertainty is 0.01, and your relative uncertainty is going to be 0.01 divided by 85.56 times 100. So, and that's going to be 0.0117. Now, if you notice the pattern, they trended to get smaller and smaller. Well, that's because this accounts for this. Comparably, this number is much smaller than this one. But if you compare this one to this one, it is a much higher number. You see how that goes. All right. So when we add or subtract values, kind of like a temperature change, we're going to take those uncertainties and we're just going to add the uncertainty, even if we're actually subtracting. So, I mean, when you do a temperature change, that delta T, you're going to do 27.9 minus 20.7 because you're trying to find the difference, right? So that value is not hard to know. That is going to be 7.8. But you were not going to subtract these uncertainties. You were going to add them. So it's going to be 0.2. And for this one, you are adding them here. So you're going to get going to be 6.47. That's going to be this number plus this number. And then you were going to add the uncertainties, and you're going to get 0.3 hertz. All right. Now, a solution is prepared by adding 50 grams of water. Now, notice the decimal point there. That means that there are 2 sig figs. And then 1.00 grams of sugar. What is the smallest graduation on the balance used for the sugar? Remember, this is a balance, so we'll just assume it was digital. We'll say that the smallest graduation was, what I'm really asking is, what is that uncertainty, right? So the smallest graduation was 0.01. And the smallest graduation used for the water, well, that was going to be 50 plus or minus 1. You see how we have a difference right here. This is grams and this is grams. Now, if we have the total mass, we're going to take these two values, we're going to add them together, just like usual. But we have two sig figs now, right? So now we have 51 grams. And then we are also going to add in our uncertainties, but the uncertainty is only reported to one sig fig. So we are going to change that to 51 plus or minus 1 gram. So you see how this uncertainty right here swallowed up this uncertainty. So no matter how precise one measurement can be, once you combine it with a least precise measurement, it just all disappears. So keep that in mind as you design your experiments. Would you use a more precise balance for the mass of sugar to result in more precise total mass? Well, if this one was way more precise, if this one was 1.00000 plus or minus 0.0, and so on, would that make any difference? No, not at all. Because the precision is limited, by the H2O balance. And that's awesome. Okay.